Good day. Welcome to my autonomous car project. My name is Patrick Bray and I'll be exploring some vector concepts with you, as well as a little bit of graph theory. But we're going to be doing a little bit differently today. Remember in the pre-quarter assignment when I said I was a huge fan of Mario? Well, that was true. So I figured why not use Mario Kart to show off what I've learned about vectors. So I picked a flat course because we're working in 2D, and let's get started. The course is mapped out on a grid, and if you look in the bottom corner you can see the path Mario is going to take. He starts, obviously, at the starting line, which I've just made 0, 0, the origin, but this is a race, so obviously he can't stay here. So Mario heads straight up to point B, which on the graph I have marked 0, 3. That gives us a vector of 0, 3, because there's no horizontal movement, that's just 3 units up. But the track doesn't end there. There's a turn here, so Mario turns and starts moving to point C, which is at 1, 3, just 1 unit over from where he just was. But that gives Mario a diagonal of 1, 3, which is, of course, the result of adding vector AB and vector BC. The diagonal takes Mario from point A directly to point C in one move, at least on the graph. The race isn't over yet, though, and we can do the exact same thing for the next couple of segments. From C, Mario heads diagonally down to point D at 2, 2. So from C, he traveled on a vector of 1, negative 1. On the graph, that's 1 unit right and 1 unit down. Then Mario drives straight across to point E, which is at 3, 2. So he traveled on the vector 1, 0. There were no units traveled vertically, so it's just 1 unit to the right. If we add these vectors together, 1, negative 1 plus 1, 0, that gives us a diagonal of 2, negative 1 from point C to point E. And just like that, we've gone that much further along the track and avoided all of the dirt. Let's continue on and breeze through these next few segments. To go from E to F, Mario moves right 1 unit and up 1 unit, so he moves on a vector of 1, 1 to reach 4, 3 where F is. He then goes straight across to point G at 5, 3, and just like from D to E, he only moves 1 unit to the right, no vertical movement. And all we did was add the vectors 1, 1 and 1, 0 to get 2, 1. Alright, Mario's done pretty well so far, but he's got a very sharp turn in front of him now. He came to G moving on 1, 0, and now he heads straight down to H at 5, 2. So the outgoing vector is 0, negative 1. To find the direction change, here we use vector subtraction. If we call the outgoing vector u and the incoming vector v, then u minus v gives us the direction change. And since u minus v is the same as u plus negative v, we just flip v to get negative 1, 0, and add it to u. That gives us negative 1, negative 1, which is the other diagonal of the parallelogram, and that's our direction change. From H at 5, 2, Mario drives diagonally all the way down to point I at 3, 1. That's a vector of negative 2, negative 1. Now visually you can see that this is a diagonal move, but how long is it actually? That's where norms come in. If Mario wants to figure out exactly how far he has traveled, then he'll need to find the norms of all the vectors. Let's just start with H to I. Let's just use d for distance, and we just have to find the square root of distance x squared plus distance y squared. That's just like Pythagorean theorem. Let's do it. Negative 2 times negative 2 is 4, and 1 times 1 is 1. 4 plus 1 is 5. So we just find the square root of 5, which when we round gives us about 2.24 units. And that is our norm for that segment. And we can repeat this process for every single segment on this entire track. And then if you add them all up, you can figure out exactly how many units Mario will travel in this race. So, spoiler alert, this track will have Mario traveling about 21.3 units. Let's get back to where we're at the race, shall we? Mario's at I, and Mario makes another turn and heads diagonally over to J at 5, 0. That's a vector of 2, negative 1. But this is a sharp turn, and Mario is going to be asked about it in the press conference after the race. Just how sharp was that turn? Well, using the dot product, we can figure that out. The formula is simple. It's just the cosine of the unknown angle, or theta, which is what that Greek symbol means, equals a times b divided by the product of their norms. So we take negative 2, negative 1, dot 2, negative 1. We multiply the x components and add the product of the y components, which gives us negative 4 plus 1, and that's negative 3. We then divide the product of the norms. The norm of negative 2, negative 1 is root 5, and the norm of 2, negative 1 is also root 5. So we do negative 3 divided by 5, which gives us a cosine of negative 0.6. And lastly, we take the inverse of that cosine, which will give us an angle of about 126.9 degrees. That is a very sharp turn, and Mario took it with style. Mario now arrives at J and makes yet another turn, going straight down to K at 5, -1. Just like the last time we went straight down, we are subtracting vectors. The outgoing vector is 0, -1, and the incoming vector is 2, -1. Coming from I, same as before, we change u minus v to u plus -v. So we flip v, which is 2, -1, and that becomes -2, 1, and add it to u. That gives us -2, 0. The other diagonal of the parallelogram, and our direction change at J. Okay, so here's Mario's favorite part of the track, going from point K to point L. Mario reaches K at 5, -1, and normally racers would take a safer path, avoiding the dirt, which would cause him to go extra points at 3, 0 and 2, 0, before being able to reach point L at 0, -1. But Mario isn't like most racers. He is the jump man, so he uses the mushroom to take this shortcut, avoiding those extra points, and going directly from K to L, with a vector of -5, 0, straight across. And on the graph, that's just 5 units to the left. Now, Mario doesn't realize it in the moment, he's too busy winning, but he just did scalar multiplication. In the direction Mario is going, the unit vector is -1, 0, just the length of 1. If you multiply that by the scalar k equals 5, you get 5 times -1, 0, which gives you an answer of -5, 0. And that's the full vector Mario took by doing the shortcut with the mushroom. And finally, there is one last turn at point L, 0, -1, and Mario heads straight up back to the starting line, which is also the finish line at 0, 0. Mario traveled on one final vector, 0, 1, going just 1 unit up. Lap complete. Wahoo! Now that Mario has finished racing, let's take a look at the whole graph again and analyze it using graph theory. The path Mario took around this track is a connected graph. That's easy to see. No isolated edges, every checkpoint is a vertex, and each segment Mario drove on is an edge. Now let's take a look at the graph. Is it an Euler circuit? Well, every single vertex on the track has exactly 2 degrees, and in order for it to be a circuit, none of the vertices can have an odd degree. Since none of them do, this path is in fact an Euler circuit. But that's not all. Mario also went through a Hamilton circuit, which means that he passed through every vertex exactly 1 time and then ended up returning to the starting vertex. Mario hit every checkpoint from A to L exactly once before ending back at A. So Mario's lap counts as both an Euler circuit and a Hamilton circuit. And to top it off, the guy was driving on a race course called Mario Circuit 3. Circuit is the word of the day, I guess. And that's the race. Thanks to Mario, we covered a variety of vector concepts today. Hopefully this made those concepts a little more fun to talk about. Thank you so much for watching my project.